And this is going to be a very important topic because many of us have developed bad habits, myself included, over years using Python, and we've inadvertently made our code slow. And so if we do things a little smarter, we can speed it up. And so the goal of today is to um, demonstrate the ways that we get past this. So here are the learning objectives. So this is kind of the kickoff webinar for a series of 3 workshops. So the learning objectives today, I'll begin with the verb describe. So you will be able to describe some of these techniques and some of the main concepts today as a result of the webinar. But when you take the associated 3 workshops, you're going to get your hands on doing this stuff. And so in that case, we're going to change those verbs to do, right? They're going to be action verbs at that point. And so today, though, we're just going to set the framework of what we're covering in those workshops and show the benefits and the why and sort of the underlying theoretical framework, okay? So today, really what I want you to be able to do is go away with this thought of describing a Python loop replacement strategy. So you're going to search and destroy your loops in Python, and you're going to replace them with something. And so those replacements will be NumPy constructs. Now, many of you have probably used NumPy like every day. If you're using Python, you probably, I use NumPy all the time. Really? Okay, well, we'll see. Many of us are, and we have done this. But many times we continue to use NumPy in an inefficient way through a Python loop to access the elements. And so you're going to say, well, what do you mean? Well, you're going to see. And the idea today is that this loop replacement strategy will improve the readability and the maintainability of your code. It'll typically reduce the size of your code, make it easier to find where those errors are, if there are, and it's much more readable, it's maintainable. It's faster on the current existing hardware, and it will be faster on future hardware software accelerations that are built onto those lower level libraries that access the Intel hardware. So one of the things you'll be able to do is describe the NumPy clauses to aid aggregations, reductions, broadcasting, using where and select clauses. A lot of times you'll have embedded logic conditionals that would prevent your code from effectively vectorizing. And so I'm going to introduce you to a couple of NumPy constructs that let you do that anyway. And so there's some real speed ups that you can get from doing this. And so the other thing we'll do is, you'll understand the AI Analytics Toolkit and just the underpinnings of the lower level libraries that are constituent parts of that, including this whole aspect of NumPy. And so this is what we're going to do. We're going to kind of get a lay of the land. And so, the first thing is I'm going to be using the AI Analytics Toolkit. You can actually, these constructs that I'm going to be talking about today are built into the stock versions of NumPy. And when you do the lab, you're going to see 1 or 2 lines of code that you can use to show that you're using the underlying. It turns out that it's going to be using the Intel oneMKL libraries under the hood. But that's one of the things that you can fiddle with. And so I want to make sure that you understand the value of using NumPy in this way. And so, but if you just take the stock versions of NumPy, you're going to be getting a lot of the benefits, or essentially all of the benefits that I'm describing right now. However, the reason that I introduced this chart is because the AI Analytics Toolkit is an umbrella over a number of AI related concepts and libraries and frameworks. And so just like I described that we have optimized the stock versions of NumPy that you would just get when you do a pip install or you do a conda install of NumPy, we've also put accelerations by default into the TensorFlow and into the PyTorch communities and into those frameworks as well. And of course, TensorFlow and NumPy sort of inherit, if not directly, they inherit the goodness or the benefit or the conceptual framework of NumPy under the hood, albeit in a tensor sort of a mode rather than just the n-dimensional matrix sort of idea. And so all this kind of stuff is built into those stock versions. And we offer these optimizations around deep learning, for example, which I'm kind of talking about now in the upper left corner, the TensorFlows, the PyTorches. If you want to do, compression and do quantization and optimization of a deep learning model, we have Intel Neural Compressor and so forth. Machine learning, a lot of us are dealing with tabular data and unstructured data such as documents and so forth. And so, a lot of those common libraries that you would use, the Intel extension or the scikit learns, we have an extension that accelerates that. And XGBoost, the stock version of XGBoost is actually implemented with a lot of these same principles under it from Intel. So you inherit those. But all that being said, the cadence at which TensorFlow or PyTorch or XGBoost or whatever these communities are, the cadence at which they adopt these optimizations into their main lines for you to use as stock is typically slower than the rate at which we create these optimizations at Intel. And so the value of the toolkit is that you get exposure to the latest and greatest, fastest ways to do these things, but you're not hobbled, excuse me, in a sense, by using the stock version. We are pushing as much as they take these things in their cadence, in their roadmaps. We offer these things to those communities to put into the main lines. So I just wanted you to be aware of that. And so specifically with respect to my discussion today of NumPy, I may touch on SciPy and we'll probably touch on Pandas. These two libraries are impacted especially because we've impacted the NumPy. And so Pandas kind of inherits from that, SciPy and so forth. So I just wanted you to kind of get a sense for the feel and for the lay of the land that you do get these benefits from the stock versions, but sometimes there's extra sweetness by doing the library. And so this is just kind of a restatement of the same thing, a little bit more drilled in. I'm going to go past that for sake of time. So NumPy, powered by oneAPI. So I've already alluded to the fact that the stock version already has this built in. But if you want the toolkit, here's where you can get a link to go download that and play with it, okay, for the actual toolkit. So the idea here is that, are you getting, now I know you're using NumPy. I guarantee almost everybody on this call, you've got examples of your Python code and you're using NumPy. Why this talk? Okay, well, because I'd like to ask this question. Are you using the NumPy effectively? And I think you're going to see in some of the examples I'm showing you, and particularly when we start doing the labs, you're going to notice, you're going to recognize old behaviors that you've done, and you're going to say, oh, I'm still doing that. And this is going to try to encourage you not to do those things, okay? And so are you using NumPy effectively? And we'll describe what that means here directly. One of my admonitions or my encouragements to you is to keep your NumPy library up to date. So, you always want to make sure you're doing the update condas and then update your NumPy. Keep those things fresh because the latest and greatest goodness will be coming through those updates to those libraries. Excuse me. So let me just say from a personal perspective, I think Python is great. I used to be a Fortran programmer way back in the day, and then I converted to being a C programmer and then a C++ programmer back in the days. And that was all well and good, and I loved it, and it was fine. I made the switch to Python because I got away from programming for a little while, and when I came back, I just found it a lot faster and easier to prototype an idea, especially in AI and data science, using Python. It's so great at doing string manipulations. You're not doing these very low-level stir-toke, kind of things and stir compares and writing nested loops to do certain string manipulation functions because a lot of this stuff is already built in Python. I love it. Just even the fact that I don't have to bother with types, that's I can just start running and playing, and so stream of consciousness, it's very easy to get going. You can find examples all over the place, of how to tackle a given small level routine. Heck, you could even go to, Chat GPT and have it generate, Python code for you to solve some small problem, convert a PDF to text, or whatever. So it's very easy to find examples. That dynamically typing thing makes programming easy, right? It's really easy to do. I don't ever think about my memory management and freeing my memory, and so it's kind of a lazy man's language where I can just program quickly. I've done some really amazing prototypes of ideas very quickly, just in a couple of days, that probably would have taken me several weeks or a month to do in C or C++. And so part of that is that I'm rustier back in those languages now, but there's just some inherent goodness. However, as we all kind of know, Python can be slow. Generally, you're not going to put a Python program head to head against a C program and hope to win a race. You're just not. That would be silly, right? And so Python is slow, but it's slow for some certain things, especially. Okay, it's slow for repeated low-level tasks. That means loops. Okay, so you've got some loop that's doing some low-level task, or large loops, where the trip count is billions or something, or nested loops, matrix multiply type, triply nested loops, or if these kinds of things, where ultimately you have a large trip count. If you were to unroll all those loops, you'd have a large trip count. List comprehensions, even if the size of the lists or arrays are large. But there are ways to mitigate this, and the one-word answer to it is NumPy. Okay, and so let me just show you why these things are a problem. I'm going to start with a kind of a quote from Wes McKinney. Now, he's the inventor of Pandas. Okay, so he has a little bit of an idea of numeric manipulations in Pandas, and his idea, his statement here, is this practice of replacing explicit loops, which I'm going to be showing you today, with array expressions is commonly referred to as vectorization. So this is a little bit different idea. It's related somewhat to vectorization when we think of that concept from C++. Certainly, there's an aspect of the C++ SIMD vectorization, and I'm going to be touching on that today. But this topic of doing the array expressions has a more general sort of view in Python land than it does in C++ land. It's very explicit and surgical in C++. It has a little bit wider connotation in Python. So, but this practice of replacing those loops with array expressions is referred to as vectorization. In general, vectorized array operations will often be 1 or 2 orders of magnitude, according to him, faster than their pure Python equivalents, with the biggest impact seen in any kind of numerical computations. And I hope to back his statement up with some of the things and examples that you'll see today, but certainly in the labs. When you come to do the labs, you're going to see this, okay? Now, this is something that you will see when we do the lab. And so, you can hear that these speed ups, and you hear this theory, vectorization is, can speed you up. But it's not just theory. It really works in practice. In fact, I gave this talk about 6 months ago, and a fellow from Airbus Canada was listening, and he had some stress analysis code. Now, he's a Python programmer, he's a data scientist, and he took a lot of the airframe stress codes from the standard packages that generated the data, and then he was doing something in AI around that. And it was horribly slow. And so his colleagues are saying, well, you can't do anything about it. You are going to have to rewrite this whole code in C, okay? And he's not a C programmer, so he was not real thrilled. But he took these ideas right here, and he got on his stress analysis code a 60x performance. He wrote me back in LinkedIn on a comment, and he was just doing backflips. He was very excited that this stuff actually worked for his actual code. So I'm not promising that you will get that, but I'm promising you should go look and see if you don't get some better performance, okay? So, so why are these speed ups so dramatic? Well, part of this is that whole topic of vectorization that if you're a C+ programmer, if you have some of the background, if you understand anything about SIMD vectorization or some of the hardware instructions that Intel provides, AVX 512 instructions, or AVX, say starting way back, 256 instructions, or or 512, AMX, these low-level kind of hardware, things that are done at a hardware level and maybe a clock cycler that handle, very wide vector register widths. This is the sort of the classic definition of vectorization, and certainly NumPy takes advantage of that through the MKL, through oneMKL. Okay, so the idea of it here is that, let's say that you're, on an older Xeon machine that's equipped with AVX2, so it's the register widths and the vector lanes that you have available are 256 bits. Okay, so that means that if you're doing floating point calculations, you can do 8 floating point calculations at a time per core, per thread, basically. You can do 8 floating point computations if you're using SIMD arithmetic under the hood that typically MKL would do. However, when you just pick that code up and then run it on a more modern Xeon machine that's equipped with AVX 512, your registers are twice as big. So now you can compute 16 floats in one chunk per core. That's per thread, right? So you automatically, just by moving your code, this is that future-proofing thing. As you move your code forward, you get a benefit from the vector widths, but you also get benefit of the new instruction sets that we create to do clever things against those wide vector widths. Okay, so that's one reason, but that's just one reason why this stuff speeds up. The other reason, and sort of a bigger reason really in Python, that the Python loop constructs and lists and stuff are costly, and this is a huge one, is that Python is dynamically typed. We all love it for the ease and the simplicity of writing code, but what that means is you take a Python list, and a Python list, element 0 could have an integer in it, and element 1 could have a floating point in it, and element 3 could have an image in it, and element 4 could have some other object in it. So every time that in Python you go to traverse that list, it has to do a type check of some kind and say, what operations are even legal? He wants me to add 1 to everything here. Okay, I know how to do that for ints. I know how to do that for floats. How do I do that for an image, right? What do you do? And so the fact that types is the Wild West in Python in terms of, you don't have to type anything. Well, that comes at a cost, because there's this background task that have to run. There's reference counters just for an integer. An integer isn't just a simple integer in Python. It's more like an object. It has reference counters and so forth. And so when you're accessing these things, you have to ask yourself, what type are you? What operations are available on you? Oh, and so you have to go through this logic every single time you touch it. And so when you're just doing simple things with small little loops, you don't notice it. But when you're doing billions of operations, that cumulative tax of doing the same thing over and over and over and over, when you should already have the answer, with respect to the types and stuff, is a problem. And so the more loop iterations that you have, the more that this exacerbates the problem. And so the other thing that complicates it is that it's the effect of non-contiguous memory. Now this is huge because the integers even, and when you get a list, you do a C array, you just get sort of lulled into this assurance, because typically in C, when you malloc some memory, or you use a statically declared array of some kind, you get contiguous memory. Okay, which means that element 0 of a one-dimensional array in C lives right next door to element 1. That's not true in Python. Okay, it may by luck happen, but as a general rule, it's not true. So you get this list that has the elements 1 through 8 in it, and they could be spread out in memory all like this. Okay, and this turns out to be very, very, very costly. It could be hundreds of clock cycles of time every time you try to access one of these things. And again, for small trip counts, 10 or 100, maybe it doesn't matter. Okay, but for large nested loops or large loops where you're doing number crunching, and a lot of our data science projects are like that. Okay, you pay a significant tax. Now, the good thing is we can keep all the good parts of Python, and we can just get performance library, NumPy, to handle the bad aspects for us, right? But we have to know how to use it effectively. Now, one other thing, and it's related to that cost of the memory, and this is related to cache lines. The modern computer architectures are designed so that when you, it's called cache locality. so that when you read one element of an array, there's in typical coding patterns, you're very, very, very likely to be using the next consecutive or some within some distance, some stride. You're very, very likely to very quickly, very soon to use memory that's very closely located to that. Okay, and so what it does is modern hardware typically will bring in a cache line. Think of it as a carton of eggs. Okay, so think of it as a carton of eggs that holds, let's say, 16 eggs in a 512 vector register machine, AVX 512 Xeon machine. You can compute 16 floats at one simultaneous boot, and it would bring in a cache line, let's say, of 16. Okay, so that's a carton of 16 eggs. So now let's just play a scenario here. Let's think of a silly scenario. You invite people over to your house. You're gonna be watching movies all night, and so you have your rooms, and everybody, you're gonna say, "Oh, just stay at our house." Okay, great. So now the next morning you get up, and the first person comes down, and they're hungry, and they want an egg. So you take out a carton of eggs from the fridge, you put it on your counter, you take out one egg, and you start to cook it. Well, then another person comes down, and that was egg number 1, by the way, right? Well, the next person comes down the stairs, and they say, "You know what? I don't want just any egg. I want egg number 18. And so this is like Python. Python didn't put things out logically. So you have to go back to the refrigerator, you grab another carton of eggs, you put it on the counter, you take out egg number 18 and you cook it. And then somebody else comes down and says, "I'm really hungry, but I had my eyes on egg number 17,403. And you look in your refrigerator, and gosh, it's not there. You have to go to the Walgreens or the CVS or so whatever on this weekend morning, buy a carton of eggs and come back. Now this is very analogous. This means that it's not even in cache. Like, you have to go to main memory to grab this memory element, and then you come back and fry it. Well, what happens is over time you build up this. Your counter is only so big; it can only hold so many cartons of eggs, and pretty soon you start knocking them on the floor, and they break. Okay, so it's a very inefficient way to cook eggs. Okay, far better is if we get some synchronicity going here, where when folks come down for their eggs, you say, "Okay, you're person number 0. We're going to cook you egg 0." You pull it from the carton, you fry it up. Next person comes down, you get egg number 1, you fry it. They get egg number 1, and you use the entire carton of eggs efficiently and very quickly, and you cook up a whole batch, and then you go to the next carton of eggs. And that analogy is very similar to the difference between accessing memory using a lower level C primitive that is aware of contiguous memory, aware of cache hierarchy, aware of the high level optimizers in the compiler to do these kind of cache level optimizations and do it very efficiently, including even permutating your loops and doing various loop enrolls when necessary. Whatever, it knows how to do it the most effective way. That's similar to cooking these eggs in a very smart way, rather than just letting them crash on the floor, which is what Python does. Okay, so these are the underpinnings of why Python is slow. Okay, for typical numerical computations. I love it still, and I'm still a programmer because I can take advantage of NumPy. So arrays of integers in NumPy are contiguous because we're leveraging, it's basically written in C, if you want to think of it that way. And so when it allocates, and you give it, and it knows types. So typically, excuse me, when you specify a NumPy array, it can give you one by default of a certain type, but you can configure, you can tell it explicitly, no, I want int 32s, or I want float whatever, right? And so you can tell it that the nature of that data for that array. And so, the type stuff is kind of handled, and you can manipulate it easily just through the function call when you set up the array. Okay, and so this gets around this whole egg carton crashing on the floor business. You don't have those, those egg cartons crashing on the floor. That's called a cache line eviction, and they're costly. Going off to main memory is costly. So if you're going to go off to main memory, don't bring back one egg. Let's bring back a whole chunk of cartons of eggs and put them in the fridge. And then the next thing we do is we bring one carton of eggs out of the fridge and we cook up everything in the carton. So we do it in more of a block fashion. And that's highly efficient, and it can be orders of magnitude faster doing, accessing memory that way. That's the underlying, really the big underlying reason why you get these speed ups using NumPy.
Hey, Bob.
Yes, questions?
Yeah, just we'll take a small 1 minute for questions. So I see a question saying, how do we find this type of Python handling the memory access? Is there any documentation or information available to understand this type of memory accesses?
Yeah,
Python.
I came from a background of knowing the C++ side of it, so I kind of knew. There are, if you go to PyCon, there's not like, I haven't found the one definitive reference, so I found examples and discussions from, I think Jake Vanderpla, University of Washington, I think had some discussion maybe on it, maybe at a PyCon, maybe it was in his book. There's not like one complete reference, but this is, and I'm sorry, maybe we should write a book. Let's all get together and we'll contribute and we'll write the definitive book. I have not found one yet. So that's why this talk and these labs, when you come back to do the labs in the few months following, you're going to build this intuition into your fingers. Okay, so you're going to learn about it. So yeah, these there's several different topics that I broke this down into. One of them is universal functions, or called ufuncs, and we'll see what those are. So one of the ways that we can replace an entire loop with function call, and effectively the loops are built into it. You can't get away from it, but it's built into it, and it already knows how to take advantage of the high-level optimizations and the cache hierarchies and which SIMD instructions you can use, and all that kind of stuff is done for you. And so ufuncs is going to be your friend. The other things we're going to cover today are aggregations, fancy indexing, broadcasting. So fancy indexing, some of you may know, but some of you may not. Broadcasting is something that maybe you guys know, maybe you don't. It's hit or miss. There's no, typically when you take a class on Python, they don't necessarily cover every one of these topics all the way through. NumPy, where, and select. When you're handling conditionals, when you have conditional logic in your loops, how can you vectorize it? Okay, well, we've got a way. And so I'm probably not going to go into our all loops vectorizable discussion, but we'll this is kind of the general idea of the flow for today. So just to get started, baby steps, here's some simple ways to create a NumPy array, typically from a Python list. So you can create them without the list and populate them in whatever ways you want, reading them from data files and so forth. But a lot of times, those of us that are writing data science code, what happens is you typically write some little proof of principle, proof of concept code, and you start with data that's like 100 elements by 100 elements in some 2D array or something, and you write your algorithm and you prove that the algorithm is working, and okay, all that's great. And you didn't notice the slowness because it was kind of smallish, but then what happens is, great, the idea works. And so now your array sizes go from 100 by 100 up to 1,000,000 by 1,000,000, and all of a sudden you're waiting hours and hours and hours for the results to return. And it's directly related to these kind of ideas. So if you can replace those access patterns by using the NumPy array, so this is how you can create them. You can create them pre-filled with zeros. That's kind of like a calloc or whatever. You can specify to stuff it with ones. You can stuff an array with the identity matrix, for example. There's lots of ways that you can create arrays, and you can explicitly give it a type. Now, you notice that up here in the top line, I didn't give it a type, and I think it defaulted to float in this particular case. Down here, I can explicitly control the type that it is. And so now ufuncs. Now, I'm going to rattle these things off, and even as much as I rattle this off, and I'm going to speak quickly, I cannot exhaust the list of things. This is just an example set of lists of the kinds of things that are covered by NumPy ufuncs. The point of this is that if you look, you're very likely to find some function that does something. If it's a low-level routine you're trying to do and you're doing it within a Python loop, you got a good chance that it's already been solved and already done as a function. For example, adding a couple of arrays together, addition, subtraction, multiplication, division, reciprocal, matrix multiplication, log, exponent, square, all those transcendental functions, sine, cosine, tan, arc sine, arc cosine, the hyperbolic tangent, the inverse hyperbolic tangent, the radians, degrees, converting, all those kind of things, all those trigonometric functions, bit twiddling functions like bitwise and bitwise or and bitwise XOR, all those bit twiddling things. Comparison functions is something one array greater than, less than on an element by element basis. Is it less than, equal to, all those kind of things. Floating point functions, is it infinite? Is it an and? Can I compute F absolutes on everything? Just automatically do it against the entire array. All these things, floor functions, ceiling functions, all these kinds of things. So there's more than we could spend an hour just talking about the kinds of things that are built into ufuncs that are already vectorized. Okay, so a ufunc is a vectorized wrapper. Now in vectorized, now I'm kind of going back to more Wes's definition, and it includes this idea, even though in C++ or in C, you may look at a code snippet, a little kernel, and say, well, that has an anti-dependency. There's no way I can, or a flow dependency, or not a flow, but an anti-dependency or something like that that would prevent me from parallelizing, from vectorizing. Well, you still get benefit typically in Python doing the same kernel, because you at least get the benefit of the cache locality and the memory contiguous memory aspects. And so a lot of times, that's what I mean by vectorized in this context, is that it includes that goodness that comes from just having contiguous memory and high-level optimizations in addition to those SIMD kinds of things. So be aware of that mapping in your brain, that vectorization in NumPy and Python world is a little bit kind of like a superset of what we mean by vectorization when we're coding in C and C++. It has some of the same aspects, but it's broader because in C and C++ we tend not to think of high-level optimizers and cache locality and then those things as being part of vectorization. It's not typically handled or discussed that way in C and C++ books, but that is the way it is in Python land with NumPy. Okay, so implementations, vectorization, supporting automatically AVX 512, AVX 2 and 512, and further back in time, SIMD instructions and so forth, but it'll use the latest and greatest ones where it makes sense. And so it takes a fixed number of specific inputs. So the thing about a ufunc is that it's kind of well defined in terms of the API. It produces a fixed number of specific outputs. So it's typically a very specific function that you're trying to do. So like for in this case, the NumPy trunk command. It is just going to truncate those digits. And so we get -3 and 3. Now this would be, if we were doing this on 1 billion elements, it would be very, very fast compared to doing this in a NumPy loop. I'm going to show you some examples, but this is what a ufunc is typically, that list of things, and it has specific set of inputs, specific set of outputs, and it applies element wise. Okay.
Hey, Bob.
Yes.
Can you explain what is fancy indexing, and how it
yes,
can
I'm going to get there.
using...
I'm going to get to fancy indexing, and this is actually kind of part of an example of it right here. Okay. This is, so good timing. Here's an example where I'm going to write a loop to just say, just give me a new list that gives me every other element, all the even elements of an original array A. Well, I can compute this thing on the left. That's about the most efficient way I could think to do it in Python without using fancy indexing. And so that code on the left sort of becomes that code on the right. At least the loop on the left becomes the code on the right. You can specify A colon. So we're saying that I'm going from, I didn't specify the initial index before the first colon. So just give me all the elements there. So colon, it's basically a step size. So colon means step size of 2 in this particular case. Now, if you're dealing with time series data, which a lot of times we do in data science, you may think, well, I don't really compute, odds and even things. That's more of a math thing. I tend not, we don't see that in the real world. But you typically do see this kind of a thing when you're dealing with weekends. When you're dealing with time series data and there's a difference in behavior of the weekdays versus the weekends, then you would use something like a : 7. You could say 0 : 7 and say get all the Sundays, and 1 : 7 and you get all the Saturdays. So you will find ways that this becomes helpful. And in this particular example, on the dev cloud, when I was running it, I was getting about a 4.5x speed up for just 100 million elements, which is really not that big. So, but these kinds of things, and the thing is that this seems silly maybe, but I would challenge you to go back and look at your code and see how many times you've got a for loop that does some small little thing, whatever it is. And I'd almost bet, even not seeing your code, that whatever it is that you're doing there, you can probably find a ufunc, an aggregation, or something, or a fancy slicing to do it faster. So I just encourage you to do that. So these are some of the aggregations. The aggregations could be called, a ufunc as well, but aggregations really typically have this extra connotation that you're reducing a dimension of some kind. So when you're doing a sum, or you're doing a mean, typically you take a big 2-dimensional array and you say, I want the mean. Okay, well, you get one single value as an output, but you gave it this n by n or n by m, input. So you're reducing the dimensions on the output, right? And that's typically what we mean by an aggregation. So when you have a mean, a standard deviation, variance sums, these are all topics that we deal with every day in data science, right? I mean, hopefully you're not doing any loops where you're, manually, doubly or triply nested loop computing the standard deviation or the mean. I'm going to show you some examples in the labs where if you were to do it that way and then compare it against doing this way, it's incredibly faster to do it the smart way, and it's much more readable and maintainable. But these are the kinds of things. Cumulative sums, we use that all the time. When do you use it? Well, for example, now these tend to be smaller, but if you were doing something like a principal component analysis and you had 50,000 columns of data, and then you said, well, give me 1,000 principal components. Okay, well, then what you might want to do is do a scree plotter. You want to see the most significant, typically they're going to be ordered, and you would add them together in a cumulative sum and plot it to see where your point of diminishing returns is. How many columns do you actually need to get 90% of the variance of the data, or whatever it would be? And so these kinds of things are done most effectively doing something with NumPy like this. And so these are just some of the examples. So aggregations are vectorized. Now in this case, we're taking this code on the left, and we're just doing this what looks like a sort of a cumulative sum. So we're just summing up all the values in that array, and then we're taking that sum and dividing by length. So this is a mean. We're computing the mean. And but to do it with NumPy, you take that same NumPy array. Now, in this case, we had it as a list. We could have had that as the NumPy array. That's fine. It would be the same code. But and then you just say, take A, which is my array, and I say :mean, and there you go. You get your answer. But there's more to it than that, because I can, and we'll see in some examples soon, that you have more control with vectorization. You don't have to get just that one single scalar when you do a sum. If I was to do a sum of all these elements, 7 and 7 and 7, that'd be 21. The sum of this A array over here would be 21 if I just did a sum. But if I say compute the sum along this following axis equals 0, then what it does is it computes a partial sum for basically each column in that array. So 4 plus 1 is 5, 5 plus 2 is 7, 6 plus 3 is 9, and so forth. Or I can shift the dimension and look the other way, saying axis is 1. And so now 1 plus 2 plus 3 is 6, 4 plus 5 plus 6 is 15. And so you can manipulate these things to get more precisely what it is that you're after without having to have convoluted logic and loops. Okay. So this is just an example. This is, and many of you are probably using this kind of thing in your code, but we're going to find more and more and more examples. And some of you may not be doing this. I know that I was at another company several years ago, and I was just doing stream of consciousness programming, trying to get some algorithm to work. And I did this kind of thing on the left, because my loop sizes were small. My elements were like 100 by 100. And so I just did this because it made sense to me, and I just did it. Well, then that proved it on the little case, and then I had to move it to the big case, and now instead of 1,000 by 1,000, it was 1,000,000 times 1,000,000, and the thing was chokingly slow. It's just awful. It's awful. And so sometimes it pays even up front to just do this thing right away. Use the NumPy array and just do it this way. This is more readable, it's more maintainable, it's faster on current architecture, it's going to be faster on future architecture, it's just better. And here I'm getting 100x speed up. In a future generator, if I would move this to new hardware later on, I'd get it probably even more speed up. But this is the tax that you pay for using Python loops to access this numerical data, even if this numerical data is a NumPy array. And that's why I'm saying, are you sure? Just because you're using a NumPy array, if you're accessing it with a Python loop, you're probably building in inefficiency, and it could be gross inefficiency. So go take a look. So NumPy, this is aggregation statistics. This is just a way of doing a cumulative sum. This was roughly 13 times faster for me on the dev cloud that we'll be doing in the labs together and next time we meet. The NumPy broadcasting. Now this concept begins to stretch the muscle memory in your brain a little bit. If you want more discussion of this, what I would do, I've mentioned Jake Vanderplaa's name before already. Jake Vanderplaas is prof, I think, out of University of Washington, and he wrote an excellent book on data science from scratch. I would recommend it. But specifically, he created a video at, I think it was PyCon, probably 2017 or so. And he described it probably in more detail because he goes into it for an hour, just this idea of broadcasting. And it's a great video. I would really recommend that you watch it. But let me just explain what it is in layman's terms as best I can. So from linear algebra, you can't take a 1x3 matrix and add a, let's just say a scalar to it. Those dimensions don't match, okay? But what we mean by it, we do it all the time, because what we mean by that is that, let's say I want to take the number 2, and now in this case, I'm going to do an element-wise multiplication. It could be an addition, either one. But let's say the multiplication example I'm showing you here. I want to multiply every element of that by 2. Well, in linear algebra, that's legal. You can multiply a scalar times a vector or times an array, that's legal. The addition in linear algebra is not, you're not allowed to add a scalar, in the strictest sense, you're not supposed to do that, right? Like you can't add a 1x3 thing to a 3x3 thing. That's not allowed, okay? But we're going to work on this together. Let's think about it. Let's try this multiplication example first. What I'm going to do is I'm going to conceptually, now it doesn't mean that it actually does this in memory. It may do it in the register or whatever, but it's going to effectively stretch that single element of the 2 conceptually. You see it ghostly there, the 3 2s. So I stretch it to match the dimensions of the other argument, A. Now I can element by element multiply those together. I get my 2, 4, 6, and there's my result. So conceptually, this is the idea of broadcasting. This is at the baby step level, okay? But what we can begin to do is to, and hopefully I've got this one, yeah, right here, expand this idea so that I take a 4x3 entity and I want to add a 1x3 entity to it. Well, you don't do that in linear algebra. If you're taking a linear algebra class and you try to do this, they're going to slap your hand. You're not going to get full points because those dimensions don't match when you're doing a plus operation. But what we mean by that, right? There's the literal syntax of the math, and then there's the, well, what do we mean by that? Well, what we mean by that is I want to take the 1, 2, 3 elements, that 1x3 vector, and I want to add it to every single row of that original matrix. Well, conceptually, I can do this idea of the stretch. I can take the 1, 2, 3 conceptually. What I do, I'm not saying that this is what actually gets done in memory underneath the hood, but conceptually, you basically can stretch those elements so you have copies, theoretical copies, conceptual copies of the 1, 2, 3, going all the way down so that now the dimensions do match, right? Now you can add them, no problem, and then you get this result. This is the example of broadcasting. Now, broadcasting really does, at the bottom of the day, take advantage of those SIMD instructions, the bit twizzling, and all that kind of stuff to do these operations very effectively and very efficiently. Okay, so here's a way of doing the same thing, but stretching in 2 dimensions. So in this case, think of this. I've got a 4x1 matrix. I'm trying to add a 1x3 matrix to it. Now think about that. Wait a minute, you've got a column matrix and I'm trying to add a row matrix to it. I've got a row column vector and I'm trying to add a row vector. You can't do that. Well, it depends on what you mean, I can't, because conceptually, if what I mean is I want to take the 4x1 matrix and basically I'm going to stretch it, conceptual copy, to make a 4x3 matrix so that the 2 dimensions will begin to match. We've got a 4x1 and I got a 1x3, so I'm going to convert the 4x1 to a 4x3 by copy or stretch. And now I've got a B1x3. I want to make that a B4x3, so I'm going to stretch it the other way. And now I have a 4x3 and a 4x3. I can add those together and I get a result. So I'm stretching both arrays. This is this idea of broadcasting, but it can be very powerful. It's not used every day. You probably won't use this every day, but I show you in the lab some examples of how you can do this. And for example, doing outer products. Sometimes, mostly we try to avoid outer products like the plague, but sometimes there's a reason that we want to do this outer product for data science and to do different things. And so this is one very effective way of doing that and controlling it then with some conditional logic later that I'll show you. So here's a broadcasting example here where what I can do is I can just reshape this matrix. So in this case, I'm going to create a simple multiplication table. And if I were to do a simple multiplication table, the way I would do it on the left is through Python code. If I do this on the right, I can just take a matrix A that has shape, 1 by n, and I can reshape the A right here to be, let me see if I can do my laser pointer thing here. Will that show? Okay, go previous. I don't know how to get the laser to show, but anyway, the A reshape n by 1 basically forms a transpose of that matrix A. And so now I've got a n by 1 entity multiplied by a 1 by n, which gives me the outer product. This gives me a multiplication table. Okay, and so when we use this in conjunction with what's called the NumPy where clause or the NumPy select clause, I can get conditional logic to take place. So the where clause doesn't have to be just used in broadcasting. It'll be used on any NumPy array. And the idea is, instead of writing a loop where I'm going to go through and say, if the value of my A array is less than 5, do one thing, otherwise do something else. Okay, I can encode that. Yes, question?
Yep. Why do we use reshape rather than transpose?
Yes, reshape is fine. And that's what I did in the previous example, as I did reshape. You could do the transpose. And now it's just a question of which one is faster for you. In my particular case, this turned out to be fast, but it's essentially the same thing as a transpose. So it's just up to you to choose which is your favorite cup of tea. Do you like green tea, or do you like chamomile? It's personal choice, and you do some testing. This one, I just, for whatever reason, I can't remember why I used reshape, because typically I do use transpose, but yeah, either way. So right here, what we're doing with the where clause is we have a condition A less than 5. So if any element of array A is less than 5, what I want you to do is return back to me a new array. And if the value of A is less than 5, then you're going to just give me back the original contents of A for that condition. Otherwise, return back to me 10 times A. Okay. Now, if you're to do this in a loop, this would be probably an order of magnitude slower if you're doing this in a for loop. If you just do a NumPy where clause, what this does, and notice right here that I've got the original A's was 0 through 9. Every time that the values were less than 5, I copy back the original array, 0, 1, 2, 3, 4, 5. But when the value was greater than 5, I returned 10 times that value. Now, again, where would you use something like this? It could easily be used in something like time series data, where on the weekends or the weekdays, there's no business being conducted, or somehow it's a difference. So maybe you blank those zeros out for the Saturdays and Sundays, or whatever it would be. Time series tends to have this periodicity to it, and so doing things like this is not uncommon, for things like that, where there's differences in the way you handle certain data, right? And so, or for example, let's say that you do a DB scan. You're doing a clustering operation. The nice thing about the scikit-learn, and we have Intel extension for scikit-learn that does that faster, by the way, but let's say you do DB scan. And so you're looking at a cluster of data. And the nice thing about DB scan, by the way, is that if it can't kind of fit anything into a cluster easily, given the EPS and the number of cluster size that you give it, 2 parameters, what it does is if it finds some extraneous dot, some extraneous piece of data that it can't quite say, well, it doesn't really belong to cluster 1, 2, or 3, it's its own thing, it's an outlier. Well, it assigns a class of -1 to that value. So typically after you run DB scan, you'll have things like class 0, 1, 2, 3, 4, and -1. -1 class means that it's an outlier. Well, typically you want conditional processing to happen on those outliers. So you could use something like this NumPy where clause to say, wherever the array is less than 1, do something else with the data, right? The normal cases, go ahead and do our processing. So this would be a way of vectorizing that so you don't have to use the loops that are going to slow your way down, okay? So it's things like that. Now in the lab, I show you an example. It's just a really contrived example where I said, well, the pandemic was going on. There was a bunch of stuff. So I just said, well, let's look at the California housing data set and let's just come up with some scheme, right? We'll say that somebody, let's just pretend, came up with a scheme to say, okay, we're going to stimulate the economy, California housing data. We'll give a rebate on the sale price of a house. The state will just magically come up with the money and do this to, rebate on the sale of a house in California. If the buying price was between $250,000 and $350,000, then you get the rebate, because we're trying to be targeted in our deal, in our promotion, or whatever it would be. So how would you do that? Well, if you do it with a for loop and you just try to do it as efficiently as you can with just for loops, and you go through and do the data, versus doing a condition like this, I can do a where clause. So here's what the loop would look like in a Python loop. But if I get rid of the Python loop completely, I can do the same function by doing a NumPy where clause. And I can build in the conditional logic choices here. If the price is less than a high price or greater than a low price, then return the result where, okay, you get $50,000 off the price in the one case and you don't otherwise, or whatever, right? So it's a contrived example, but these are the kind of things that happen quite a bit in business situations. I've done consulting with telco companies in the past, and telco companies typically have promotions, all the time. So they have a promotion that goes for the month of whatever, and so a particular year. And so they have promotion after promotion after promotion after promotion. And so basically they encode that in columns. If you think of it in terms of a spreadsheet, which is not really the way they do it, but if you think of it in terms of a spreadsheet, they would have column after column after column of manipulations of the data, one for each kind of a promotion thing, because some people got double promotion, some people only got promotion A, but not promotion B, and this thing just builds, right? And these are all handled basically in SQL databases, but conceptually, if you were to glom it all together, that's what it would look like. So being able to do something like this, where you specify these conditions, is very salient, particularly for large tabular data in real business settings like telcos and stuff like that. So the NumPy where clause, the idea here is that we can find the row and column indices, very, very quickly. So I can find out where the outliers are, for example. In this case, if I wanted to find DB scan, I did a DB scan on my cluster data, and I want to find all those outlier classes. That is, all the places where it assigned a class of -1. Well, then I can look at my DB scan array. Anytime it's less than 0, I could print those values as being, outliers, but I could specify the row and the column indices. And so I could do that as a for loop, or I could do it just as this where clause. And, the where clause is basically encoded right here. NumPy wherever that scan is less than 0, that's the array I'm interested in. Just print the column or the row here, I guess. And then DB scan, if the array is less than 0, just give me the 1 column. It would do that there. So I get the row index and the column index wherever those outliers are. So and so on. I mean, this is just kind of a contrived example, but DB scan is one of these things that you would want to handle conditionally. So for example, let's take the matrix multiplication table. We created one using we're using broadcasting. We multiplied 2 matrices together, an n by 1 and its transpose. Okay, so we have an n by 1 times a 1 by n. That's an outer product. That's an n by n matrix. It's filled with values, and it happens really, really fast. Okay, but let's say, I want to modify that. I want to use conditional logic such that I want to replace, if the multiplication table, if blank out, make 0 everything except the entries where the multiplication is divisible by 12 or 9, right? And so if it's divisible by 12 or 9, keep it in the multiplication table, otherwise get rid of it. And so in basically one line of code right here, you can do these kinds of things. You're handling conditional logic to do sort of more complicated-ish things in the array, okay? And this is much faster. In this case, it's like 20 times faster. But sometimes the NumPy where clause gets ungainly too. It's just hard to wrangle, and that's because the conditional statements get complicated. And so one of the things is big brother, if you want to think of it that way, or its big sister, is the NumPy select clause. And so really let me go to the next slide where it will probably show better. So right here, I've got a for loop, and I've got this weird conditional logic. I've got an array A, and it's huge, right? But I'm going to look at the 4th column. If the 4th column is 10, I'm going to assign the 5th column to be some computation. If column 4 is less than 10 and column 4 is greater than 5, I'm going to do some other calculation, and so forth. I've got this weird logic, okay? If you're trying to do this in a Pandas apply statement, by the way, it's going to slow you way, 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 way down. And in our lab, we're going to show you how to accelerate this an example very similar to this against Pandas itself. And we're going to get a couple orders of magnitude speed up on the apply statement by doing this. But anyway, this is the idea that instead of that logic up above, I replace it with the down below. Now, I'm going to argue that the thing down below is more readable and more maintainable. The idea is you create a condition list, effectively, that has tuples in it of the conditions that you want. So you have, when A is less than 4 and A is, greater than or equal to 5. That's one condition. The other condition is that whenever column 4 is less than 5, that's my other condition. So I have this condition list. Then I have a choice list or an action list, the thing I want to do as a result. The thing I'm going to assign a result to an array as a result of calling the select clause. So which things am I going to give you based on the condition? Which things am I going to choose or action am I going to take? So in this case, I take the choice where I say A comma 2, plus A comma 3. That's the 0th element of the choice. So therefore it matches the 0th element of the condition clause. So those things get bound together. The element 2 of the condition clause gets bound to the element 2 of the choice clause. And then I have a default clause. So if none of those conditions hold, I'll apply the default. So I can replace this logic up above with this thing down below, and I call one select statement, and this is 20 times faster in this case. In that Pandas case that you're going to see in the lab, if you come back and do our workshop, I think this is going to be the 2nd workshop where we tackle this. You're going to see amazing results that we get even on applying this to a Pandas data frame. And we'll do it 2 different ways: on the Pandas data frame as the data frame itself, and on the Pandas data frame after we then convert that to a NumPy array. But in both cases, we can still use the select clause on it, and it gives really cool, fast results, and it's more readable, maintainable. And this is the idea. Pandas is built on top of NumPy. I alluded to that Wes fellow, the inventor of Pandas, and so he's aware of these kinds of things. But all these kinds of things are built on top of NumPy. SciPy, kind of the same thing. And we're going to be able to get an apply statement to really speed up handily in lab number 2 and workshop number 2. Workshop number 1 is going to be more of these kind of things where we're going to do broadcasting. You're going to get your hands dirty doing broadcasting, doing aggregations, doing ufuncs, and seeing and practicing that muscle memory of how to do this on your own data sets, so that hopefully you, like the NumBus guy, can go back and refactor your code and potentially get some big gains. So this is the just some of the examples using NumPy as an alternative to the Pandas apply. So if we're trying to apply this lambda function to a Pandas data frame, and here's the function we're going to try to apply is func. Func itself calls something called my function, which is a slowly executing log function. And so how would you do that? Well, I could instead of that, I could do this. I could create a condition clause like I just explained. I could create a choice clause. Oh, I'm pressing the wrong button. I want to see if I can't get that laser pointer to show up, but I don't see how to do that. But the condition clause, you give it a condition clause with your logic in it. Then you say, well, what do you want to do as a result of the condition clause? That's your choice values. And then you just call select, and it automatically creates the array, sorting all that logic out and giving you that resultant array. And this exact thing, doing it with Pandas with an apply statement versus doing this way, I got a 200x plus speed up. So it was quite a good benefit. So anytime you have that conditional logic in a Pandas apply, this could bail you out. So so anyway, these are just I don't think we have a poll for the audience. We're really coming up on the end of this thing here, but I just wanted to leave you with a call to action. The call to action is go search and destroy those large loops. What do I mean by a large loop? I mean if it has a large trip count, a singly nested loop with a large trip count, a doubly nested loop with even somewhat smaller trip counts. But if you enrolled it, it would be a large trip count. All these kinds of things, doubly, triply nested loops, any of those kinds of things, you want to and probably can replace it with either something directly in NumPy or the thing built on NumPy called SciPy, where maybe you're doing a spectrogram, or you're doing some set of eigenvalues, eigenvectors kinds of things. You can do that with SciPy. And it's built on the lower level NumPy constructs underneath, or scikit-learn. So we have that Intel extension for scikit-learn. And so a lot of those common things that you would already do, higher level thinking, higher level abstractions, such as dbScan or k-means or principal components, or any number of classifiers, support vector classifier or regressors, support vector regression, random forest, any of those kind of things. You would use those at the high level. So search your loops and replace them. Get rid of those Python loops. Call some function that somebody's already done that work for you. Any way you can do it, okay? Now, the other thing I didn't explicitly mention here, but we're going to see it when we do the lab, first workshop, list comprehensions. You're going to read that, list comprehensions are the way to go. You're going to find some advice, and they're great, and I use them. I use them in my code. But use them with temperance. Use it for things where your trip count is 10 or 100. Don't use a list comprehension for things in the millions or probably even in the thousands, right? If you're using a list comprehension, there's still a pretty good chance you can do a NumPy equivalent and you're going to beat the snot out of it in terms of performance. So list comprehensions are faster than the Python for loop that I was showing you. But they're going to be on the order of maybe 10% or something faster. They're not going to be 10x faster or 100x faster. So look for the NumPy equivalents if you can. So even if you're using list comprehensions and they're big, replace them. right? And if you have if statements, you have conditional statements, you have conditional logic in your Python loop, can you vectorize it? Well, I've given you a couple of choices, a where clause and a select clause. And even with fairly sophisticated and complicated logic, you can use a select clause to do operations where, against the entire arrays, kind of in one fell swoop. So I would recommend that you go refactor your code, look for these opportunities. And so that's